This is my second video about the best methods for reducing ketones to secondary alcohols. In this presentation, I'll show you some examples of the reduction of ketones with alkali and other metals. Although borohydrides are often more selective and cause less side reactions, metals such as sodium or aluminum are inexpensive and their use as reducing agents can make sense in certain instances. Before the discovery of sodium borohydride and lithium aluminum hydride, the reduction of ketones and aldehydes by metals was the only available method besides hydrogenation. Ketones were usually reduced by sodium or zinc in alcohols and aldehydes by zinc, iron or sodium amalgam in acetic acid. Today, a number of additional procedures are available, but the main issue of these reactions remains the avoidance of pinacol couplings. The reduction of ketones by metals is assumed to proceed as sketched on this slide. Single electron transfer leads to the formation of carbon-centered radicals, so-called ketyls, which form aggregates of two or more radicals. Even strongly electropositive metals are not able to reduce these ketyls further to dianions. In the absence of protic solvents or acids, these ketyls can dimerize to form pinacolate salts. Pinacolates are not very stable and may be cleaved by strong bases during aqueous workup to yield mixtures of the starting ketone and a secondary alcohol. Careful acidic workup, however, usually yields the expected pinacols. Sterically demanding ketyls may also disproportionate into secondary alcoholates and enolates. The latter can undergo aldol addition and condensation with the starting ketone to yield mixtures of oligomers. In order to obtain a high yield of secondary alcohol, the reduction should be conducted in the presence of proton sources. Protonation of the ketyl would yield a neutral radical, which is much easier to reduce by single electron transfer than a metallated anionic ketyl. Because most metals will also react directly with protic solvents, careful optimization of the reaction conditions may be necessary to keep the required excess of metal as low as possible. The main advantages of the reduction of ketones by metals are that no anhydrous solvents are required and that some metals are quite inexpensive. Once suitable conditions have been found, these reactions are also relatively easy to perform. More problematic are the amounts of inorganic waste produced by these reductions. Then, owing to the high reduction potential of many metals and the intermediate formation of radicals, these reactions are not always clean and many other functional groups may react too. Because of the direct reaction of metals with a solvent, a large excess of metal is sometimes required, what further increases the amount of waste. This is an old example of a typical reduction of a simple ketone by sodium in aqueous ethanol. Only slightly more than the theoretical 2 equivalents of sodium was required. According to the authors, the reaction is highly exothermic, and one side reaction responsible for the moderate yield was the formation of condensation products if the reaction temperature rose too much. In this more recent example, cyclohexanone was reduced by zinc in the presence of ammonium chloride as proton source. Unfortunately, a large excess of both zinc and ammonium chloride was used, and it isn't clear if this could be avoided by further optimization. This is again an example of the reduction of a cyclic aliphatic ketone, this time by lithium in the presence of catalytic amounts of an iron salt. The product was isolated as benzyl ether, which is easier to extract and less volatile than the corresponding cyclopentanol. Copper, nickel and cobalt salts also catalyze the reduction of ketones by metals of the first, second and third group and suppress the formation of pinacols. As already mentioned, the most problematic competing reaction during metal reductions of ketones is pinacol formation. This happens particularly readily with aromatic ketones, as shown on this slide. However, not only the structure of the starting ketone, but also the choice of solvent and additives determines if mostly secondary alcohols or pinacols are formed. On this slide, I've summarized some of the conditions which cause either reduction or pinacol formation of simple aliphatic ketones, aromatic ketones, diaryl ketones, aliphatic aldehydes, and aromatic aldehydes. Pina means pinacol coupling and redu means reduction to secondary alcohols. The numbers in brackets refer to the references on the next slide. Conditions which only lead to pinacols are colored in red, whereas the green fields indicate clean reduction to secondary alcohols. Blue fields indicate mixtures of products. In general, the tendency to yield pinacols increases when going from potassium to sodium to lithium to second group metals and then to third group metals. The solvent and additives are, however, more important for the outcome of these reductions than the choice of metal. This table shows that aprotic conditions mostly lead to pinacol formation, no matter which metal is chosen. In the presence of protic solvents or acids, however, either clean secondary alcohols or mixtures of alcohols and pinacols are formed. There are also instances of pinacol formation in water, but this may be due to the low solubility of some starting materials in water. Such reactions are biphasic, with the reaction mainly taking place in the organic aprotic phase. Aromatic ketones and aldehydes can yield complex product mixtures upon treatment with alkali metals, in particular in liquid ammonia as a solvent, because also the arenes may be reduced by single electron transfer, such as for instance in the Birch reduction. Alkoxides produced by the reduction of aldehydes can cause the formation of esters by Tishenko reaction or of carboxylates by Cannizzaro reaction, if water was present. Liquid ammonia is less basic than solutions of alcoholates in alcohols, and in liquid ammonia no epimerization of secondary alcohols by sequences of Oppenauer oxidation and Meerwein reduction are usually observed. In alcohols, however, such epimerization can readily occur if the reactions are allowed to proceed for too long. So, for most aldehydes and ketones, it seems to be possible to find suitable conditions for a clean reduction to secondary alcohols or for clean pinacol couplings. As mentioned above, transition metal catalysis may be used to further enhance the yield of secondary alcohols. These are the references for the previous table. Besides pinacol coupling, a number of other functional groups may be reduced or otherwise transformed by alkali or other metals. Olefins, alkynes and arenes can all be reduced, for instance by alkali metals in liquid ammonia. Similarly, most organic halides can be dehalogenated by metals such as lithium or sodium. Reactive ethers such as epoxides, benzylic or allylic ethers can also be cleaved by strongly electropositive metals. Metallic lithium can also be used to debenzylate N-benzyl-amides. Then a number of sulfur derivatives such as thioethers, sulfoxides and sulfones undergo carbon-sulfur bond cleavage in the presence of alkali and other metals. Further functional groups that are readily reduced by metals include nitro groups and carboxylic acid esters. One little-known reaction of nitriles is their reductive decyanation by sodium in aprotic solvents, which yields sodium cyanide and alkyl or aryl sodium compounds. Nitriles may, however, also be reduced to aldehydes or primary or secondary amines. Amines are also the main products when oximes or pyridines are treated with sodium. In the Clemmensen reduction, aliphatic or aromatic ketones are treated with zinc in the presence of concentrated hydrochloric acid, whereby alkanes are obtained, probably by intermediate formation of a zinc-carbene complex. Finally, ketyls may add to olefins or alkynes, both intramolecularly and intermolecularly. Thus, unsaturated ketones may cyclize or oligomerize upon treatment with electropositive metals. Here are some more examples and 2 review articles on the subject, mainly concerned with the stereochemistry of the reduction of carbonyl groups in steroids. In the next video, I'll present to you the Meerwein-Ponndorf-Verley reduction, which is way more selective than the reduction of ketones with alkali metals. Nevertheless, for some simple ketones, sodium, zinc or aluminum may still be a competitive alternative to other reduction methods.